A very good morning to everyone. So, in continuation with our last class, we'll discuss about spectroscopy. Before we do that, that day we have seen about the electromagnetic radiation. So, today we'll see how electromagnetic radiation is absorbed by molecules or by matters. Okay, so this part is known as absorption of electromagnetic radiation. Okay, now before we proceed with the absorption or how absorption takes place, if we look back at the different category of electromagnetic radiation, we have the X-rays. Now from X-rays, what we get the information is the single crystal structure. This is rather a very new topic and widely used now by organic chemists, where you can determine the structure of a molecule. Then we have the UV visible, which is usually used for the presence of multiple bonds. So the more the double bonds or conjugation in a molecule, then you can understand that from the absorption spectroscopy of UV visible. Then we have the infrared. In the infrared, it gives us information about the functional groups, because this is related to the vibrational frequency of molecules. So we'll be doing in more details about all these technique. Then in the radio wave, interestingly, it gives us important information about NMR, ESR. Okay, I'm sure you have heard about MRI, which is one of the very important advancement in medical science, known as magnetic resonance imaging, which is actually NMR. Okay, it is actually NMR, but in a 2-dimension and 3-dimension. Also, we'll not go into detail of that, but magnetic resonance imaging is nothing but the same technique of nuclear magnetic resonance, or NMR. So from this technique, we will be able to deduce the structure of a molecule completely. Okay, so different absorption take place for different levels. UV visible is mostly absorbed by double bond, presence of multiple bonds. Infrared is absorbed mostly by vibration of or stretching of frequency of different functional group. Okay, so what is this absorption of electromagnetic radiation? Now, initially, historically, we can say, if we look at this solar spectrum, okay, so if you take the sunlight and then you diffract it with a prism, you will not find a continuous spectrum, but you'll find something like this, where you have some dark lines in between. Okay, so you have, like, say, the KH lines, the G lines, the F lines, then the D lines, and so many. Okay, so this puzzled scientists, like, why do we have dark lines when the sunlight is supposed to have all the possible spectrum from the whole range of the electromagnetic radiation? But it was found that there are some ions that are present in the surface of the sun, which absorb specific radiation. Okay, absorb specific radiation with some range of frequency, and that's why it produced these dark lines. So not only that, we also have emission of electromagnetic radiation. So if you supply energy in the form of a heat to a particular molecule, they will emit radiation, but the radiation that they emit will not be the whole range of the spectrum, but rather only in some portion, like, say, in this region. This is for helium. Now you can see that they emit certain radiation at certain. This is a superimposed image of the whole spectrum along with those lines which helium emits. Okay, so why does molecule absorb only at certain frequency, or why do they emit only a certain frequency. So that will lead us to the absorption spectroscopy. Now, if we consider this, any molecule can be represented in this form, where we have the energy in this direction, and then we have the states of the molecule. It can be the electronic state 1 or the electronic state 2. Okay, so these are the electronic state of a molecule. The first electronic state is known as the ground state. The second, here in this case, is known as the excited state. So these two states are the states of a molecule. So what happens is that when a molecule can absorb energy only if the energy is equivalent to this difference. Okay, it can only absorb energy when it is equivalent to that difference. Okay, so if suppose the difference is delta E, then if the delta E is equivalent to a particular frequency h nu, okay, then this molecule can be excited to a can be easily excited and jump into the first excited state. Okay, so that is absorption. That's why it can absorb only a specific frequency which correspond to that energy difference. Okay, if the energy, suppose your photon energy is less than this, if suppose this delta E is only this range, then it will not be able to excite the molecule from the ground state to the excited state. So that was the difference. Now at the same time, you can supply the same energy not in the form of light or electromagnetic radiation, but you can supply this energy in the form of a heat. You can excite the molecule into the higher energy. So what happened in that case is that a molecule that is present in the excited state, when it comes down to the ground state, it emits radiation which is equal to the difference in these two energy. Okay, so from absorption we can also have emission of radiation, just like we have seen absorption of radiation by the different ions in the sun, and also emission of radiation by helium. Okay, so molecules can absorb energy in such ways. So what you can do is that you can, in say UV visible technique or in IR technique, what you do is that you have a kind of a scanning frequency, an instrument that can supply different frequency of radiation, and then you have a detector, okay, something like this. Okay, so you have a beam source. This is known as the incident radiation, and this is suppose your molecule, and then you have your detector. So what do we have here is that we have the incident radiation, which you know, then you have the transmitted radiation. So if you know these two things, you can know how much of the energy is absorbed or the intensity of the radiation is absorbed. Okay, say suppose at a particular frequency nu, the incident radiation is 100, and then the transmitted radiation is also 100. That means there is no absorption. Okay, but on a different frequency, this is 100, and then the transmitted radiation is only 10%. That means it has absorbed, the molecule has absorbed 90% of the radiation. Okay, so you can detect if a molecule absorb a particular wavelength or not. Now normally it's not simple that a molecule will absorb one wavelength or just two wavelengths. It could absorb a broad spectrum. Now let's have a look at this example here. We have the different frequency represented by these different colors here. Okay, so this is the incident radiation with different frequency. So first what you do is that you supply this frequency, then you supply this frequency, then this frequency, then this frequency, and so on to the source. Okay. After that, let's say out of all the frequency, only this green frequency is absorbed by the molecule. The rest were not absorbed. Okay. So the molecule get excited into the excited state. Now, on a detector side, if you plot the photons absorption versus the different wavelength, so this is the wavelength on this side, and this is the intensity of radiation, you'll find that here transmission is 100%, here transmission is 100%, but when it comes to this one, transmission is 0, so it dropped down. But this one again, transmission is 100, this one 100, and then again 100. So this is known as a transmission spectra. Okay, with a line like this, this is the transmission spectra. Or if you plot the absorption spectra, what you do is that absorption means it will be the intensity minus the transmission. Okay, so in this case there will be 0 absorption, 0 absorption, but here there will be 100 absorption, then again 0, 0. So this is known as an instrument can scan these frequency, and once it scans the frequency, it can automatically plot a graph, and then you can get the spectra. Okay, so this is how you obtain a spectra. So you will know exactly that at this point there's an absorption correspond to this particular frequency. Or if it is a transmission spectra, then you know that at this point there's a transmission, there's an absorption of transmission. Here we have a transmission, full transmission, and here is a dip in transmission. So these are known as peaks. So knowing the peaks, you can know the character of, you can easily know the character of or the property of a molecule. So you can study the different property of molecules based on these peaks that you obtain from a spectra. Okay, we have the incident radiation, then we have the photon that is absorbed, and from there you get the spectra if you plot. Okay, now let's have a look. If suppose you have an instrument that can automatically record this, if suppose this is your frequency and this side is say absorption. Now what you do is that it will automatically scan, okay, at different frequency. Then at some point there will be a peak, okay, like this. So this is known as an absorption type of spectra. Okay, but most of the time it will not be a sharp peak like that. It will be a gradual peak like this. Okay, but still you will know what would be the lambda max or the maximum absorption that take place in a particular compound. Okay, now if it is a transmission spectra, what happens is that you have the transmission is always 100%, then there's a peak when it absorbs. Okay, so these are called as spikes or peaks. So you will learn about this. So either you use a transmission spectra or you use a absorption spectra, it doesn't matter, because you will still get the value of a lambda max or the peak, and from the peak you can get the information or valuable information about a molecule. Okay, so sometimes you may use frequency, sometimes you may use the wavelength. It depends. That also will not have any differences. It doesn't matter which way. Okay, so I hope you are clear about the absorption and emission of molecules. So molecules can absorb only if the electromagnetic radiation has the same frequency as the difference in the energy level. Okay, now one last thing I would like to mention here is this. every molecule will have different molecular orbital. Okay, so like for example, we have two hydrogen atom form what is known as a sigma and a sigma star orbital. So this is an energy difference here. Of course, it's possible to excite the electron from this ground state to this excited state, but then you'll require a lot of energy, especially for sigma to sigma transition. Now, as the molecule grow bigger and more complicated, what happens is that you can have, in a simplified form, the sigma, sigma star, then we have the pi and pi star, and finally we have the non-bonding electrons. Okay, so these are the different energy levels that are present in any molecular orbital. So the transition can take place from either of these, but most of those transitions which are very low energy transition are usually from non-bonding to pi star, or if there's no non-bonding electron, then it will be pi to pi star type of transition. Okay, so we have all these type of transition that are possible in a molecule. Okay, so we'll be dealing in more detail when we go to UV visible and also when we go to IR. So this is just a little about the absorption spectroscopy and also about emission spectroscopy. What's more important here is about the absorption of electromagnetic radiation by molecules. Okay, so that's all for today. Thank you.